Hello, and thank you for having me here presenting the work of me and my colleagues. Our student Max, I'm Professor Decker from the Chair of Databases and Information Systems from Aachen University, and our colleagues from the Institute for Plastics Processing, Patrick and Mauritius, and Professor Hopman. I would start with a motivating example for our work. That is injection molding. So the colleagues manufacture plastic parts where they, as we can see here on the top right, they inject material into the mold under a very high pressure and then produce plastic parts. The machines that they get from their suppliers, they have embedded OPC servers that support data extraction. And the task for them and their colleagues is to extract dozens of sensor values, all together with very valuable metadata assigned to them. This is currently a very challenging and manual process because they need to manually inspect the OPC server, as we can see on the left. So, for example, they browse via this UI, they browse the OPC server. They, for instance, choose a injection unit, and in there they choose a particular sensor. And from there, they need to manually inspect the identifier of a node, how to get the value, and additional other valuable fields, such as the units or unit ranges, for example, value ranges for nodes. And they usually collect these in just lists of identifier, and then they apply a static data extraction OPC, and in the end, they need to rearrange the exports manually, like they need to match the nodes with their particular metadata afterwards. And our vision is a more flexible capturing of these informations. And for this, we need some methodology to transform from a more expressive query language to this basic OPC language. And we do so by combining two areas, like two research areas. One is OPC is the open platform communications, which was a just limited and Windows-only format back in those days, and was extended by unified architecture extension. So it's OPC. And it consists of a client-server architecture, and it consists of multiple information models. So there's the core information model that just has basic data types and so on in it. Then they have companion specifications. For example, there is the Euromap that specifies node structures for plastics processing. And then on top, there are also vendor-specific extensions, which really is some pain in everyday work, because when you get machines from different manufacturers, they probably have different vendor-specific extensions, which make it really hard to have a uniform data extraction. And on the other hand, we have XPath as an XML query language that supports navigation via path expressions. So from one or more currently selected nodes, we can execute path expressions, such as child-parent relations or more sophisticated calls, as we can see here. And this leads to our vision that we would like to apply such an expressive query language like XPath to a less expressive query language or protocol called OPC. And this leads me to our methodology. It is the general methodology. So we would like to apply a more expressive query language to a less expressive query language. And our concrete concept in this work, which I'm just presenting right now, is that we first export the contents from the OPC server and generate an XML file from it, so that we are able to actually express or formulate XPath expressions. They can be evaluated on these XML files, but we also propose a methodology to be able to execute XPath formal expressions actually on OPC. And please note that I will use these 5 steps, which are here on the bottom part of this slide, throughout my whole presentation. So I will always link to these individual steps. So export, pre-process the export, we formulate the expressions, transform them back to OPC, and then actually apply them in OPC. And the first 2 steps have the following methodology. Which first starts with a challenge, because the OPC export is a directed graph, and therefore it is not suited as is for XML, because this is a tree structure. So that is, we expand every node that is in some cycle. We expand this to a complete new subtree. So basically copy entire subtrees. So we expand the tree to be able to represent this in a proper XML document. And then there's another challenge, because nodes in XML are usually ordered, while in OpenCOA they are not. So therefore, we introduce a artificial ordering by their lexicographical ordering on the OpenCOA node IDs. And then during runtime, we will handle non-unique identifier in the XML tree by continuously expanding the current XPath node selection. That is, when we on some path reach this node 8, we will also continue the query on all other nodes with the same node IDs. So this is the methodology to generate this XML file and overcome these like data structure challenges. And we will now have a look at the next steps. That is the formulation of XPath expressions. So this is a very simple approach. So data scientists, they just formulate any arbitrary XPath expressions. So we do not only support a subset of the XPath query language, but we support the entire XPath query language. And we then basically transform these expressions to OpenCOA calls, which we can see on the right side of the slide. So we have very basic mappings. That is, for example, parent and child mappings, which are just parameterized calls to the OpenCOA browse function. So we basically just browse forward or we browse backward to a selected parent or the child respectively from a current node. But then there are more sophisticated or composite calls like all preceding nodes or descendant or self or other calls in XPath that basically are composite calls out of the others. And we will now have a look at our implementation details, which consists of two components. The first component is a script to actually create the export from your OpenCOA server and then post-processes it, as I just explained 2 or 3 slides ago, to make it compatible with XPath. So we can actually execute XPath queries on this export. And then the second component, which is on a scientific way much more interesting, that is, we provide an extended OpenCOA client that actually supports all the 12 XPath access. Note that our implementation is available open source on GitHub, and we use Python 3 and the free OpenCOA library to conduct our implementation. The implementation in detail of the transformation to OpenCOA looks like follows. So people or data scientists, they formulate XPath expressions, such as the rather simple one we see on the screen. So it selects the node with ID 84, and then from there it calls its descendants, and then it returns all the node IDs of those descendants. And we will then, our implementation basically then transforms this to OpenCOA calls. So our extended OpenCOA client provides methods for all the 12 XPath access. So basically have a method call, for example, for descendants, but also for the other. And then we basically map this query to a function call in the OpenCOA client. For this example, we select all descendants for the node ID 84, which store this in a variable, like with an asynchronous call. And then from there, we get the attributes for the node ID, which in the end will have the same semantics as the above shown XPath query. The next part of the implementation is what I just explained, basically. So this is an extended free OpenCOA client, which has just more function calls. So the basic free OpenCOA client would only have a read and browse function. So basically, you could only call 2 functions in this client. And now we have up to 12 more methods in this client, which we can directly call from any programming environment. And the very promising, very positive, beneficial thing here is that all the programming logic is implemented in the OpenCUA client, which means that our implementation is compatible with any OpenCUA server. So we do not need any modifications on the OpenCUA server. This is especially beneficial because you usually have no really write access to OpenCUA servers, as they come shipped with the production machines that you buy from any manufacturer or any vendor. So this was the implementation and methodology of our work, and I will now come to the evaluation of our work, which will be threefold. So we will inspect execution time in the demo scenario and the real world scenario, and we will then also evaluate the manual effort that is required for data scientists or domain experts. So first of all, let's investigate the execution time. So we have a demo scenario implemented in the process simulation server, which is available online. And we use the most recent software versions, just up to date, on a rather normal laptop, like a Windows laptop with 16 GB of RAM and so on. And our scenario is that we extract all 4,000 plus nodes from the process simulation server. And we do this in three representative scenarios. So first of all, we basically have just the local host scenario for comparison. So in there, we have like 1 or 0 hops, whatever you would call this. We have like basically no network latency and a very high network throughput because this is localhost. And the entire extraction, like the creation of the export of the OpenCUA server, takes about 23 seconds in total. We then have the second scenario, which we call UA local. That is basically in the local network setup. So we basically have one machine contacting a network router and then contacting the other machine. This is a common production network use case where people from their laptops contact machines within the production network. And here the complete extraction of all about 4,000 nodes takes about 77 seconds. We then have a third scenario, which we call UA remote. That is basically a remote maintenance scenario over the internet, which in current hard times in the pandemic gets more and more important. So people have paths of about 11 hops over the entire internet to contact a production machine in a secure production network. And here we see the obvious network overhead of all these operations. So extracting all 4,000 nodes from OpenCUA server here takes nearly 10 minutes. The next evaluation part tackles the generation of the XML file itself from the export, so the post-processing that is heavily dependent on these node expansions that I presented before. So because we need to avoid cycles in our data structure, we have to expand our export a lot. And this is very crucial if we just do it like so, because here we can see the blue dashed line, that is all the paths that are found. And we find about 10 million paths in the export because we have all these expansion operations. And this takes up to 20 hours in total of time. And this is the dotted line. We still have like a backlog of on our stack that we need to evaluate. So we just cancel the operation here because it's not suited. Since we did some investigation on the actual node structure, we find that we have a lot of actually irrelevant nodes in OpenCUA. That is just server information or nodes we do not need that have a very, very high branching rate, but we do not need them for data extraction. So we implement a more sophisticated algorithm that actually blocks or ignores these irrelevant nodes. And then we end up in a runtime of 0.6 seconds compared to 20 hours before. And we have about 2,000 paths that we find in our export. The next part of the execution time focuses on the very last part of our workflow, where we still are in this process simulation scenario. And we have all these scenarios that we presented before, like we have the UA client, like the very local one, we have the local setup with a local network setup and the remote over the internet. And we introduce more sophisticated rules. So we also introduce combined variants for these. This means that we additionally use a local cache to reduce the network calls to the server. And here on the x-axis, we see the number of extracted nodes, which go up to 2000. And then we have the runtime in seconds, which goes up to like 20, 30 seconds here on the y-axis. And we can see that here the blue ones, like the client ones, and the red ones, like the local setups, have very little execution times, up to like less than 10 seconds. Or here the network version takes up to 20 seconds. And then please note that we have a different y-axis scale for the remote setup. So the remote setup over the internet takes about 3 minutes. So this is 175 seconds. And we can see that the combined versions that use this additional local cache for execution are only take about half the time. So here this is comparison like 180 seconds to 100 seconds, for example, for the remote setup. And the same holds here about 100 seconds to 50 seconds for the like local network setup. And now we will also investigate the execution time, not only in this simulation scenario, but also on a real-world machine, like in a real-world demonstrator. Therefore, we investigate the injection molding use case, which I presented in the very beginning, in a real-world demonstrator at the Institute for Plastics Processing. So we have a more sophisticated XPath query here that collects a whole bunch of sensor nodes. And for each of them, it collects not only node ID and the actual value, but also the unit, the respective data type, and the value ranges like min and max for the values. And we then translate this to a set of OPC method calls in our extended OPC client. And we find the runtimes that we measured here on the right side. So executing the query offline just takes like no time. And this combined local network setup takes about 18 seconds to execute the entire query, like to prepare all the stuff for data collection. And the online call, like without any local cache, like all the methods are executed online. This is still a very feasible execution time for 47 seconds to actually set up the proper data extraction. And now, we come to the final part of our evaluation, which is also very important. That is the total manual effort needed for data scientists or domain experts. So we investigate the time that is needed to actually formulate the XPath expressions or to actually set up the data extraction. So our baseline is the up-to-date scenario that the domain experts investigate or inspect the OPC server manually, and then they extract the node IDs they would like and put them in a list, and then start the OPC data extraction later. And this requires up to 60 to 90 seconds per node. This is a manual effort that is required. And if we extrapolate this to all required 166 nodes at the Institute for Plastics Processing, it would end up in a total effort being spent for this entire process to like 2 to 3 hours in total. With our approach, we have the execution time for the export and the pre-processing. That is about 47 seconds, worst case execution time. And then this we need to add the time that is actually required for people to design or formulate the XPath query that captures all the information at once. And we did some investigation there, and this takes about 5 to 10 minutes in total, which means reduce the total execution time, not the execution time, the manual effort from 2 to 3 hours to about 11 minutes only, which is a dramatic improvement. And this approach becomes even more beneficial when we now reuse that query on another machine or another vendor, because then we would just adopt the query a bit, but in the baseline you would need to manually rescan for all the nodes which are there. Let me now come to the conclusion of our work. So our main goal was to transform a more expressive query language into a less expressive one. And we changed the highly manual and static process in the OPC context in the Industry 4.0 to export the OPC servers to XML and then let people apply XPath, which is very flexible to this. And we support all 12 axes in XPath, so we have full compatibility here that allows people to flexibly capture data along with valuable metadata such as units, value ranges, data types, and so on. And it makes it very easy to actually transfer existing data extractions to other machines or especially other manufacturers as well. Our evaluation showed that we dramatically reduced the human effort from 2 to 3 hours down to several minutes only. Our implementation is available open source and is like twofold, so the export and the extended OPC client. And since we only extended the client, our solution or our approach is actually compatible with any OPC server out there because we do not need any modifications to this server. Future work especially includes a fully automatic transformation from the XPath query to the OPC method calls. And we would like to improve the documentation and the performance of our OPC clients to make it even more accessible for future work. So this was our talks, and thank you very much for your attention, and I'm very happy to hear from you. Thank you.